This is the second part of lesson 7.8. And actually, I thought as I looked at it yesterday, holy cow, 7.8 is going to take us all class. No, it isn't actually. 7.8 is actually kind of over after 2 pages. There's this page, and then there's this page. This is actually review starting already. This is like a little review lesson with one kind of part that's sort of new. I'm going to show you how to use trace, but I've actually kind of shown you this already. This is a page where we show you how to use trace on your TI. We'll go through that really fast because I know only a couple people use TIs here. So all this other stuff is basically review. There's only 2 examples left in 7.8, and then we can start again kind of getting ready for the test. So here we go. So first of all, we have a farmer. He wishes to fence a field that borders a river. There is no fencing required on the side of the field by the river. So in other words, he only has to build a fence for this line, and this line. Okay, so those are the 3 lines. I don't want to mess up my picture. So those are the 3 lines. Okay, the farmer has 100 feet of fencing, and he wants the area that he fences in to be as big as possible. So what should the length and width be? What dimensions? Dimensions means length and width. That's what they mean when they say, what are the dimensions? They mean, how long are the sides? Okay, so notice once again that these notes were created in the time when everybody used the TI calculator. And it's trying to show you, oh yeah, this is list 1 and list 2. But for us, that's still useful information because what it's telling us is that this is my X and this is my Y. Or again, this is my input, this is my output. How does width affect area? Independent variable, dependent variable, for those of you who like it and the science is better. Okay, so same thing. So I'm going to let X be width. So what if I had a width of, say, 10? 10's a good start. Let's start with 10. What would the length have to be?
Also 10?
No, I have 100 meters of fence. So if I use 10 of it here and 10 of it here, and I'm not going to keep those numbers, they're temporary. What's left for width? What's left for length? 80, right. So there we go. So, and then what would the, okay, now perimeter, do we care about perimeter? We want the maximum area. Actually, you know what, I don't even care about this. Nah. Useless information that has nothing to do with the problem, so let's get rid of it. But what's the area? Well, you know what, I guess, well, no, that's, yeah, perimeter. Yeah, we don't need perimeter. Okay, so anyway, yeah, isn't it gonna basically be 100 every time? Well, no, it's not. Because remember, I don't need to actually build this side of the rectangle.
Yeah.
Right? So it actually wouldn't be the same perimeter every time. But again, it's not what they're asking me, so it's certainly not something I'm going to worry about. But, okay, well, how do you find area? Well, area is length times width, so that's 800. Okay, let's keep going. What if I increase the width? What if I go to a width of, say, let's jump up to 25? And I'm making these numbers up arbitrarily, really. What if I went to 25? I'd have 25 here, I'd have 50 left. And 50 times 25 is 1250. That beats it. So it's better to make it less skinny, right? This would be this 10 by, that'd be a long skinny rectangle. So the less skinny it is, it seems the better we're going. You know what it might be actually kind of useful? Is let's think about the extremes of this situation. What if I made the width 0? Then I'd have 100 left for the length. It'd be just a 100-meter fence across there, and the cows would have to walk along the fence. They'd have nowhere to actually graze. But logically, I guess it's still kind of a rectangle. But of course, what kind of an area would it have? It would have no area. And of course, what if we went the other way? What if we just said, no, we're going to have, instead of a line going this way, we'll just have a line going up and down. So what if I made the width 50? So then I'd have 50 one way, 50 the other way, and a length of nothing, which would still give me an area of 0. All right, I think we're ready to plot points. We are. So we go to Desmos, or again, if anybody wants to use their TI, you can put this in list 1 and list 2, right? The length number we're not putting on the grid, we're putting in width and area. How does width affect area? And, oh, I didn't mean to do that. Hang on. Come back. Come back. Come back and then shrink. And it goes to the beginning again. And then it opens twice. Because it hates me. Where are we? This is close. There we go. Farmer. There we go. Okay. Don't do that again. I just wanted to shrink this. And then open up Desmos. There we go. Oh, wait, that's not Desmos. That's not Desmos. That's Desmos. There we go. Okay. Oh, I'm missing a couple points. What did we also have? We also had, so we have 0, 0. We have 25, 12, 50. We have 50, 0. And I had one more point. I had 10 and 80. Does it matter what order the points are in? No, not at all. It'll graph them all the same. 10, 80. And there we go. So we had 4 points, right? Okay. Now, when you do this, when you turn on the points, now right now that's the only point I can see, just like we did yesterday, that will zoom out so that we can see all of the points. And there they are. Oh, 0, 0 is not right. 0, no, that's not right. Hang on. Isn't that? No, it would be 50. That's it, 50, 0. Because, yeah, 50, 0 is the point I wanted. Sorry, I typed it wrong. 50, oh no, I got 50, 0. What's the one? What one am I missing? I'm missing the 100. Okay, yeah. Oh, yeah, 0, 0. Yeah, width of 0 is area of 0. Okay, but that one doesn't really work. Right. Yeah. Okay, I see it now. Yeah. Okay, this one doesn't actually work. As you can see, I have a nice parabola shape this way, but then this point's kind of out of the way. So I'm gonna delete that one actually. You go away. You're wrecking my parabola. And then once again, there we go. So we're just gonna use 3. Right, it's still kind of looking wonky. It's still looking wonky. Oh, it's 800. There we go. Okay, so that's it. 10 and 800, not 80. That's what I've typed wrong. Thanks for noticing. 10, 800. There we go. Oh, actually, maybe 0, 0 does work then. 0, 0. Oh yeah, now it's looking like a parabola. So there we go. We can use all 5 points we have there. 25, 12, 50, 50, 0, 10, 800, and 0, 0 all work. They're all part of a parabola. And boy, that actually looks pretty close to, maybe that is my maximum. Eh? That looks like it's pretty close to the top of the parabola. But we want to know for sure. So how do we know for sure? We do a regression. Now, I have this as list 4. You probably have it as list 1. So if you have it as list 1, then you want this number here to be a 1. I need it as a 4. I need this number to also be a 4. Again, you'd have it as a 1. Type it as a 1, please. And then also, for me, it's a 4. And there's my equation. My equation is this A value is -2, this B value is 100, and this C value is so ridiculously small that it is in fact 0. Why doesn't Desmos actually figure it as 0? Because Desmos isn't really doing algebra to figure this out, and it's just estimating based on the pixel size that it can actually graph. For those of you who remember, the TI had that problem when we were trying to do statistics. Remember, it would sometimes give us a number that we knew was supposed to be exactly 4, but it would say 3.9999999. So now it's Desmos' turn to be fooled by ridiculously small numbers that should be 0. So when I see a number like this, I just go, oh, that's 0.
Oh, okay.
So that's my equation. It's A is -2 and B is 100. So back to the equation, and we'll say my equation is Y for area is -2 for A, and that's how good my memory is. I've already forgotten what the B was. 100 plus 100b, and c is 0, so I can just leave it like that. Okay. Now, how would anybody have ever gotten this answer if they didn't have what we just had, a regression? This is doable without a regression. And again, I wouldn't make you do this on a test, but I like showing it to you. I like kind of explaining where these things come from. Think about it this way. Look at the relationship between length and width. No matter what happens to width, you take that number, double it, and subtract it from 100, and you get length. Right? How did I get this 80? I went 20 minus from 100. How did I get this 25? I went 50, because I doubled it, and minus from 100. Why am I doubling it? Well, because there's a width on this side and a width on this side. So if I choose this to be x, what does this number over here have to be? It has to be 100 minus 2x. And then how do you find area? Well, area is just length times width. So it'd be length times width. So the other way to get this answer, this equation, is to just multiply that. And if you, and if you're good at algebra, can you see how this blue equation, this black equation would work out to be exactly the same equation if I just multiplied out that bracket? So there you go. So if you had to do this without technology, you'd have to reason it out using algebra. But we had technology give us the equation. Okay, I got a question.
Can I just see the table? Because I did something wrong.
Let me go back to the table. So there's the 5 points that we reasoned out.
Okay, so my dots are like reverse.
Your dots are what now?
Like reverse, like.
Oh, did you put X and Y in the wrong place? Do you have 1250 and 25 instead of 25 and 1250?
I have 80, 850, 1250, 100, 0.
8. Okay, then you've mixed up some of the points. 80. There's no 80 on here.
It was 800 that we.
Yeah, right. Yeah, you accidentally stuck us with the length number. We want the width numbers. X are the widths, Y are the areas. And again, notice how they said if you were doing this on the TI. In fact, here, let's pull up the old
Oh,
TI.
no, because we established that the X was the width. So
X is the width. We established that. So again, if I was doing, I don't need that. If I was making a list for my calculator here, okay, I did that one yesterday, so we'll clear that out. And we'll clear that one out. Okay, so if I was doing this on a calculator, I'd have the same points. I'd have 80 and, no, see, now you made me do it. I'd have 10, 25, 0, and 50. And then in my Y numbers, I have 800, 1250, 0, and 0. And there we go. There's my 4 points. And then, remember how this works? You go second function stat plot on. Make sure that it's also the kind of graph you want, a dot graph. Make sure list 1 is X, list 2 is Y. And then when you graph it, it's probably going to, well, there. See, the same problem we had in Desmos. We see 1 dot. Now, what's the TI equivalent of, give me the magnifying glass so that it zooms in on my points? You go to zoom, and then pick one. Zoom stat would be good, maybe. Zoom stat, because we're doing a stats graph. And there we go. There's all the dots. It gave me all the dots. Now, what's the TI version of a regression? You go to stat, calculate a quadratic regression, number 5. But you have to tell it that you want list 1 for X, comma, and list 2 for Y. And then when you hit enter, it does the same thing Desmos did. It tells you that A is -2, B is 100, and C is 0. Okay. Now, so you're not getting the right A and B?
No. So I put in like the list and everything, but like my equation is not following up the rat list.
Okay, are you on Desmos?
Yeah.
Okay, do you have any other equations on? Like look up, do you have any other equations?
No.
Okay, so when you click on this, it doesn't go through all your dots?
No, it doesn't even go through any of them.
Then you've got, did you type the right subscripts? Okay, but, okay, what is the subscripts on your data? My data is 4 and 4 because I have other data going on. What numbers do you have here and here on your data? Well, there you go. That's the problem. These little numbers here, can you see where I'm highlighting? These little numbers here have to match these little numbers here. Otherwise, Desmos doesn't know what data you want to make an equation for. So there we go. Done. Okay, and now, okay, remember, the gray dot here at the top is what we're looking for. The maximum number, the maximum vertex number is 25, 12, 50. So let's go back to our question here. So my vertex is 25, 12, 50. So my vertex actually was one of the points that I picked. Aha.
Is that chart in the bottom supposed to be the chart that goes from the top there?
The chart in the bottom?
I'm sorry, not the chart that's from the top. I meant that one for that question.
Yeah, this graph is that chart. 25, 12, 50. Right there.
I did not realize that it's
25, 12, 50. And there's the other points that I had, right? What was the other one I had? I had 10, 800 right there. And what was the other points that I had? I had 0, 0 as a point. And I had 50, 0 as a point. So yeah, there's the 5 points that we had, or the 4 points. Or didn't we have 5? 1, 2, 3, 4, 5. Well, we had 4. 1, 2, 3, 4. That's not really a point. That's an equation. So we had 4 points, and there they are. Okay, so here's the important part. Do you understand what this is telling you? What is the maximum area? It's the 1250. It's this highest number of the vertex. What's the width that gets me that number? 25. We should probably put units on this. We're in meters here, right? Feet. Thank you. It's feet. So my maximum area is 1,250 square feet because that's the x value that gets you the maximum. So the width is 25 feet, and the length, now the length, I'd have to kind of go back to my chart. This is the part that's the most sort of mathematical. What's the relationship between width and length? Oh yeah, if I use the number 25 here and the number 25 here, then this length has to be 100 minus 2 25s, because there's 100 feet of fence that I get to use. So if I've used 50 of it, I still have 50 of it. So there we go. There's the farmer one. All right, we got one fairly similar but a little more complicated. A farmer has 1,200 meters of fencing and he wishes to enclose a rectangular area. Let's draw a rectangular area. And divide it into 3 parts by 2 other fences parallel to one of the sides. Say he wants to keep his goats separate from his pigs from his cows. So we have 3 parts in the field. Use the table provided to do a quadratic regression to find the dimensions that will produce a maximum area. So once again, the key here is going to be width. So if I've decided this width here is going to be x, well then don't these all have to actually be x? So if I've decided that the x lines are going to be, let's start with 0. If the x lines are going to be 0, then I have 1,200 meters of fencing to put along here and along here. So they're going to be 600 each. But of course, length times width, 600 times 0 is still 0. We can do better. Let's say we've decided that the width is 10. What's the length going to be? And then what's the area going to be? See if you can think about what those 2 numbers have to be. So if this is 10 meters long, I have 4 of them. So I've used up 40 meters of fencing. How much fencing is there again? 1,200. So I've got 1,200. I've used up 40. So that's actually 1,160. But I have to split that 1,160 by this length and this length. So I divide it by 2. 580 is correct. Does everybody get how we got that number? See if you can do it again. Pick another number. How about we pick, let's just go in order. Let's pick 20. And then let's pick 30. Okay, so I'll give you a minute and see if you can figure out the rest of that chart. And keep in mind it was pretty much arbitrary. I just decided I'd start at 0. You could have started somewhere else. Okay, so I'm just giving people a minute to see if they can think about what those numbers got to be. So how did I get this 580 again? Well, I used this 10 4 times and subtracted that from 1,200 because that's how much fence is left, but I have to still do 2 lengths, right? There's a length up here and there's a length up here. So I had to divide it by 2. So if all of these were 20s now, 20, 40, 60, 80, so that would leave me 1120 of fence to do the 2 lengths. So 560. And at this point, you might see a pattern. Every time I go up 10 on the width, I go down 20 in the length. So I don't have to calculate this one. I see the pattern. And the areas, well, this one's easy. Times the number by 10, you just slap a 0 on it. 20 times 5,600, well, 2 56s is 112. So that's 112 with 2 zeros on it. So that's 11,200 square meters. And I have no idea what 54 times 3 is. 150 and 12, 162. There we go. I figured it out. That's just mental math. Okay, so there we go. There's the numbers that we are going to graph. Okay, let's start with a fresh Desmos, so that I'm not dealing with X4 and X5 and stuff. Okay, so fresh Desmos, just to show you again how I started. Okay, how do I get a chart? This plus sign gives me options on what kind of data you put into Desmos, and I want a table of data. Now I just type in the numbers. Now remember, we don't want length, right? We've decided that width is X and area is Y. So X and Y. So plug in those numbers. So 0, 0, and 10, 5,800, 20, 11,200, 30, 16,200. And that should do it. 4 points is all you actually, 3 points is actually all you need for any graphing software to figure out what the quadratic equation is. But 4 is nice. The more points, the more accurate it can be if it has to estimate. This one won't need estimating. This will be exact. This will definitely make exactly a parabola. Because again, I could have found this by just playing with algebra too. But all right, once I have that, hit the plus sign. And ooh, this is another one. We saw this yesterday in a couple of our examples. That looks like a straight line, doesn't it? If you didn't know this was a quadratic situation, you might just ask this computer here to say, hey, give me the straight line that goes through all those points. And you'd find it's not quite perfect. In fact, don't bother typing this, but if I wanted to find the straight line, it's going to, oh, whoops, I forgot the 1. It's going to say, oh, hang on, look at that. What's it saying to me? It's saying x1 and y1 can't be defined in terms of each other. This doesn't work. Okay? Oh, because I tried to do it as a straight line.
Oh, straight line.
It's not a straight line, and Desmos just told me that. So, oh, wait a minute, maybe it didn't. Hang on. I think I forgot to use my tilde. Y1 tilde AX1 plus BX1 plus C. Oh, it does. It tries. Okay, there it is. If I didn't know it's quadratic, I can get a straight line. But look at this. Can you see this? Dum, dum, dum. It's not perfect, is it? So try again. Oops. Oh, my word. There we go. Try again, but this time, let's see if it's quadratic. Like, again, we know it's quadratic. This is the quadratics chapter. It's going to be quadratic. But if we hadn't known that, we would have seen that the dots didn't match the best straight line that the computer could get. So try a different kind of line. Try a quadratic. And there we go. Now it's nailed it. I could zoom in on these points forever, and it'll be right, the dot will be right on the line every time. Now, unfortunately, it doesn't show me all of the quadratics, so feel free to play with, I just like to kind of zoom out until I can see the whole thing, and then maybe move the screen around, maybe zoom in again. I don't care about the negatives. I mean, what am I going to put up, negative fence? And there we go. There's the equation I needed. A is -2, B is 600, C, what is this number again? 0. It's a glitch of the way it calculates. No, not necessarily. What if it does have a constant to it? What if C wasn't 0 on the equation? But certainly for this type of problem with the area of a fenced-in place, yeah, the C is going to be 0. All right, so let's go back to the question. Find the dimensions that will find them. So it doesn't even ask for the equation this time. It just wants the dimensions. So, okay, I'll write the equation down just to be kind of complete here. But y equals, what was it again? It was -2 and 600. So -2 for the A value, 600 for the B value, and the C value is just 0. So I won't bother writing +0. And then the vertex of that is, we're nowhere near the vertex yet. 150 and 45,000. So 150 and 45,000. So what is that telling us about our answer? So therefore, the maximum area is 45,000 meters squared. The width of that maximum area is 150 meters. How would I find length? Because it said dimensions. Dimensions means length and width. What are you thinking?
Just add the 150 together.
Not quite.
Oh, well.
How did I go from this 10 to this 580 again? What are your thoughts? Ah, let's see. Let's look at Desmos. If we look at the y-intercept, the x-intercept is 300. And what does that tell us? Right, that would be how much fence would be left if, or sorry, the x-intercept, let's see, no, that's how much width there would be if the length was 0, right? Right, because that's a 0 area, so length, either length or width has to be 0. So if width is 300, length is 0, but does that, let's see, does that tell us?
Well, using the equation, you find it, right?
Okay, so let's see. So I was going to say there's 2 ways you can figure out what the length is. One way is, where did this number come from? This area? Isn't area length times width? So since area is length times width, length is area divided by width. So if I take the 45,000 and divide it by 150, You're right, that's 300. So the length is 300. The other way you could have done it is you could have found it doing it the same way we found those numbers there.
Using the equation.
I took 4 of these x's. So what was x again? X was 150. So 4 times 150, which is 600. And then cut that in half. Because remember, the length, there has to be a length on top and a length on the bottom. So 300. So there's the kind of problem you should be able to do with geometry. So yesterday it was kind of like money and questions like businessy questions. This one's more of a geometry question. And that's the last kind of new thing for quadratics. So let's start looking at just kind of an overview now. This is a question I don't know if there were any like this in the homework. What if I gave you the whole graph and just asked you questions about it? Here's somebody who hit a baseball. There's the y-intercept. There's the x-intercept. There'd be another x-intercept to the left of this y-intercept, but I mean, that would be in the negative part of the graph, and baseballs don't travel backwards in time. So that's the whole graph right there. So what, this by the way is kind of a calculus term. It's okay to just call that a maximum, but we call that a local maximum because, why is it called a local maximum? Because in calculus, curves can do like this. So that, if it keeps going after that, then this isn't the maximum, it's just the local maximum. It's only the maximum around here. So you don't have to worry about that though. That's more of a calculus term. So,
I mean, if it bounces off the ground, it goes back up.
that's right. If this baseball was so springy that it ended up bouncing higher than that, then there we go. That'd only be a local
It might
maximum.
be like a rubber ball if you were to do that.
I don't know that even rubber balls will do that, right? Because
Like when you throw it.
is there any type of ball that you could throw it and it'll bounce back higher than where you threw it from? I
Yes.
guess so.
There is
Yes.
a bouncy
Like
ball.
there's
Yeah,
this
I guess
one
those super
small
bouncers, yeah.
ball that bounces around like crazy.
All right, anyway, determine the following round to 2 decimal places. The vertex. So the vertex rounded to 2 decimal places. Can you read which of those points is the vertex again?
Vertex would be 2.5.
Yeah, the one at the top. So 2.5, comma.
2.6.
Oh wait, 2 decimal places. 2.5. What's after the 5? 2.55, comma. 32.34. Okay, what's the x-intercept? Well, it gave it to us. It's too bad it labeled them. 5.12, comma 0. What's the y-intercept? 0, comma 0.45. So there we go. There's the data from this thing. Now,
Isn't the way that you wrote the x-intercept and y-intercept wrong because they look like x, comma?
well, I wrote them as coordinates, but you could just say, yeah, my x-intercept is 5.12. My y-intercept is 0.45. You're right. I didn't need both coordinates there. If you just wrote 5.12, that'd be fine. If I wrote just 0.45, that'd be fine.
No, I mean, like, wasn't there this rule that you made that it has to be like the 2 intercepts?
That's if you're doing domain and range and stuff, right? Like that you have to use brackets on domain and range. And if I ask you, what are the x-intercepts? Say I had a graph like this. Here's what you're thinking of. Suppose I had a graph like this, where that's -1 and that's 3. And I asked you, what are the x-intercepts? And you said, oh, it's -1, 3, and you did that. Well, you're communicating to me that that's a point with an x-coordinate of -1 and a y-coordinate of 3, and that's not what you mean to say. Right? You mean to say that the x-intercepts are -1 and 3, don't put a bracket around it. Okay? That's what you're thinking of. Good thinking. But in this case, I actually gave you the y and the x coordinates. All right, here's the important part of this. Can you interpret what these points are telling you? How high does the ball get after it gets hit? Which of those numbers is that?
2.55.
Is this one a height?
No, sorry.
No.
It's this one.
2.5 is the time.
Are these feet or meters?
X
Meters.
X equals time and
You hit a ball 32 meters. I guess you could. All right, how long is the ball flying for? What do you think?
5.1, 5.2
It's this one.
seconds.
Because think about it. Time of flight would be how long it takes until it hits the ground again over here. So it's this entire amount of time. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and a bit. That ball had a 5-second hang time. That's a pretty good hit. The height of the ball when it was struck by the bat.
That would be.
Yes, 0.45 meters. Do you get why that is?
Because the baseball's already like.
Right, it's where the height was at time 0. Get it? Time 0 is when you hit the ball. So how high was it at time 0? And there we go. See if you can understand why that is. Now, from the graph, we can estimate some things. And I say estimate because we actually don't have an equation. But let's estimate the height of the ball after 2 seconds. So after 2 seconds, what's the height? Well, let's see. That'd be 35 there. So that's about halfway to halfway. Not quite, so I'm going to say maybe 32. It is an estimate, right? So 32 meters. What time was the ball 30 meters above the ground? So 30 meters above the ground is here. Oh, but wait a second. Isn't it over here too? So there's 2 answers here, isn't there? So what is that time? Well, again, that's 1.5 seconds. That'd be 1.75 seconds, so maybe 1.8. 1.8 and 3.2.
My money's on 1.75.
Isn't it past the quarter mark though?
Yeah.
So I'm going to say 1.8. Again, I'm estimating. So at 1.8 seconds and, what was the other one again? 3.2, thank you. 3.2 seconds. And finally, one more. What time was the ball 35 meters above the ground? Look at the graph. It never gets that high, right? It never gets that high. The highest it ever gets is 32 and change. So, never. No.
Because if it was 0, then it would
At
be
time 0,
then it would be at 0.
at time 0, it's 0.545 meters above the ground.
That would mean it would be already at that end.
Right? It's saying what time? There is no time where it's that high in this problem. Okay, so there's one where we give you a graph. We don't even give you the equation, but we ask you some questions about it. That's a pretty cool question. Here's the same type of a situation, but we don't even give you a graph. We just give you an equation. Now, this again, these notes were made for people using a TI. If we're using Desmos, we're going to enter that equation into Desmos. Once again, let me start over on Desmos. We'll start fresh. Go back to home, and then we'll enter this equation. So we're entering the equation. Now it says h of t. It's giving it to you in function notation. You can just use y and x. It doesn't matter. So y equals negative 4.9 x squared. You could actually use h and t too if you wanted to. Plus 20x plus 0.5. I almost missed that decimal. Okay, that actually almost shows up entirely on my grid, but not quite. So I want to kind of change my view, my window here, my scale, so I can see the whole thing. So let's see, what would be smart? Well, I don't need to go, it hits the ground before it gets to 5. So I don't need to go past 5. So my x can start at, say, -1. I only say -1 because I hate it when the grid line is right on the edge of my screen. So give it a little bit of space, -1, but we don't need to go all the way to 10. We can go to 5. What's that? Well, this is the example. Like, the example is we start with the equation. We're on the next page now, yeah. Sorry. Go back to my graph. Yeah, I'm going there. Okay, yeah. Okay, and again, how did I get this little screen? I clicked on this wrench. All right, now, what about the height? 5 is definitely too short. I don't need any negatives. It doesn't make any sense to even care about the negatives because that's below the ground. So I'll just say -1 because, again, that's just kind of a me thing. I just don't like my grid line to be right on the bottom of my screen. But how high do I have to go? Maybe, let's try 10. Is 10 high enough? Not quite. 20? Closer.
50?
Too much. 30?
35?
30 is fine. 25 would have been fine, but there we go. We got it. All I care about is, do I have my entire parabola, including the x and y intercepts on the screen? Question? graph isn't the same, the equation is the same? Okay, and what is your settings? Do you have the same settings I do for the scale? Okay, now yours is a different shaped screen, so it's bound to look a little different than mine. Oh, okay, there we go. All right, so now let's actually follow the notes for those of you who want to play with your TI here. So if you're doing Desmos and you don't have a TI in front of you, feel free to skip past this and just, well, there's your graph, and you can actually fill in the blanks from Desmos, okay? For those of us who have TIs, we're actually going to do this on the TI. Hang on, I seem to have frozen. There we go. Oh, hang on. There we go. Okay, I'm going to do this on the TI. Okay, go back to the graph. Did I lose you someplace? Open the settings, yep. Okay. So I picked these numbers so that I could fit the entire domain between, well, the entire domain that's the positive side of the graph. And I picked these two numbers because I just wanted to make sure the peak was visible. So 30, you could have done 25, it would have worked. Okay, where's my TI folk? Okay, Desmos guys, you're on your own for a minute. Try to fill in all the blanks. TI folks, if you're doing this on a TI, let's go to the TI. And on the TI, okay, so clear everything, erase everything. Make sure your stat plots are off. I still have a stat plot on because of the last example I did. Quit. Start with maybe your window at normal. So that's zoom, which one's standard? 6, zoom 6, which gives you your usual -10, +10 grid. Now let's go to the stats, or to the plot, the y equals, and put in our equation. So what was it again? It was -4.9 x squared plus 20 x plus 5, plus 0.5, sorry, plus 0.5, 0.5. And then when I hit graph, same problem Desmos had. I can see the beginning of my graph, but not much of it. So I want to change my windows. And now, how do you change the window on this? You go to Window, and you just do the same thing I basically did with Desmos. You kind of play with it. You go, okay, well, from here to here, 0 to 5 maybe? So I'm going to change my window from, say, again, maybe -1 to 5. Get it? X minimum, X maximum. From -1 to 5. Scale, SCL means scale, so you're counting by ones. And then Y minimum, again, we don't need any negatives, so I'll just change that to -1 so that I can see my grid nice and easy. And the Y maximum is too small at 10. And if you tried 20 and graphed it, it would still be too small. Here, let's see, we'll show you. So I try 20, and then we'll hit graph. Oops, 20 I says, and we'll hit graph. See, oh, it doesn't quite show me my peak. So go back to Window and change it from 20 to say 25. Is 25 enough to see the peak? Yay, we got it. So that's it. So I'm going to say that I've got my window settings are my X minimum, I said, from -1 to 5 with a scale of 1. Now, when would you change the scale? You're putting a very big strain on your calculator to make it count by ones if the graph goes up into the thousands. So then I change the scale and say count by 10s or by 20s or by hundreds. Okay, Y minimum is, again, -1, and the maximum went to 25, and my scale is 1. Scale can stay 1 until you get into really big numbers. And the graph should look something like what we just did there. Although this person obviously set their scale to Y maximum to 40. That's why they have their grid so far up. Yep. Okay, so now, if you're, okay, I'll be back to Desmos in a second. Now, if you're on the TI, now that you have your graph, and it's so pretty, what if you want to find the vertex? You go second function, calculate, which is the trace button. And which one of these is the vertex? Why doesn't it just say vertex? Make our lives easier. Nope, 0 is your x-intercept. Think about what the vertex is in this situation. It's the maximum. So there you go. So your vertex is your maximum. And just like always with this thing, it'll only find a point if you give it like a zone to find it in. So move to the left of the vertex, hit enter. Move to the right of the vertex, hit enter. And then it's going to guess. Ignore the guess, hit enter again. And there it is. X here is 2.04 and Y is 20.9. So 2.04 and 20.91. So there is our vertex. And you guys on Desmos should have been able to find that pretty easy. Okay, so back to Desmos. From this equation. You didn't type it right if it's not a curve. I don't believe you. There you go. Okay, so you've got yourself a vertex of 2.041 and 20.908. So we're going to put that as our vertex. So 2.04, comma, 20.9. I'll just use 3 significant digits there. X-intercept. Okay, Desmos people, how do you find the x-intercept? You point at it. There it is. There it is. TI people, how do you find it? Second function, calc, 0. Your zeros are your x-intercepts. And then again, you have to say which one it is, so go past it. Now, this is hard. The stupid numbers and letters are in the way. But look at the numbers. You know you've passed the x-intercept going to the left if you end up negative for the y number. And then hit enter. And for the right boundary, just keep hitting the cursor until you're positive. There we go. Y is positive 0.9. I must have crossed the intercept. And there it is. It's, oh, that's hard to read, isn't it? X equals, I almost can't read that. X equals negative 0.24 or something. Is that right? Negative 0.0. Oh, there's a 0 there. Negative, wow, this is terrible on mine. Oh, well. Anyway, let's see what it is on here. Negative 0.025, so that's what it's going to be. So I'm going to go back and say my x-intercept is negative 0.025. That's one of them. The other x-intercept is the more important one, because in the context of the question, we want to know where this ball hits the ground. So 4.106 is the more important number. That's why they say x-intercept. They kind of assumed you didn't care about that one. So it's 4.11. That's the one we care about.
How do we find this without?
Now, how do you find this one with the calculator? Hold on. Let me show you the calculator again. On the calculator, I want the other x-intercept, so I go calc, my 0. Hang on, let me finish doing this. And then the left boundary, I have to go past, get close to it. Come on. Here's another good reason why you should set the scale to not be 1 sometimes, so it doesn't count so long. Okay, there we go. We're still positive for y. Enter. Go past the x-axis, and now it's negative. Hit enter. And there it is. 4.11. Same thing we can see on Desmos. Okay, question.
I wrote both different y-intercepts.
There's only one y-intercept.
Yeah, but like I wrote negative 0.025.
This is an x-intercept, not a y-intercept. Okay? On the graph, you can see, zoom in if you'd like, right? This point here is the y-intercept. That's an x-intercept. So here it is. So it's actually 0.5 is the y-intercept. Now, how do you find the y-intercept on a TI calculator? It gives you the steps right there. Trace and then value. So you say to the calculator, you say, we'll trace or calculate a value, which is number 1, when x is 0. Because the y-intercept happens when x is 0, and it just finds it for you. Okay? The maximum height of the ball is the y value of the vertex, which is 20.9. The time of the flight is the x-intercept at the other end, right? The far end, the 4.11. So the time of the flight is the 4.11. isn't it? Or no? Am I looking at the wrong one? What was the x-intercept again? Oh, no, sorry. The x-intercept, yeah, 4.11 is the x-intercept. So the time of the flight is 4.11 seconds. The height of the ball after 3 seconds, I can find the same way that I found the y-intercept. I can just say to it, okay, I would like the value of this thing. So second function, calculate the value when x is 3. And it'll just tell me it's 16.4. For those of you on Desmos, if you want to know the height of the ball at the 3-second mark, there's 2 ways you can do it. Let me go back to what I had before again. What did I have before? I had -1, and what did we say before? 5, and we had -1, and I think we said 25, right? There we go. Okay, so how do I find, what am I looking for again? Oh yeah, the height of the ball after 3 seconds. So how do I find the height of the ball after 3 seconds? Well, here's the easiest way to do it. Just drag a cursor. But if it's hard to land right on 3, like, you know what you can do? Is you can graph x equals 3. And there we go. It crosses it for you. 16.4. That might be easier than not having this on here and trying to find, well, where do we exactly hit 3? Oh, no, that's not quite. I lose my patience for this very quick. Trying to land right on 3. No, that's too big. No, that's too small. Ah! Just graph that. Where do they meet? 16.4. And the same thing's true for the next one. The next one wants to know, when was it 10 meters above the ground? Why don't you just graph y equals 10? And there's 2 places at the 0.549 second mark. And what's the other one? 3.533. And if you had to do that on a calculator, you do it the same way. So I'd break out the calculator again and I'd say, okay, I would like to graph another line. How about I graph the line y equals 10? TIs don't let you graph x lines. But that's okay, because they have a way to do x lines. You just hit value. But if you want to graph that, you just type in that, graph it, and then look for see if you can tell which one it is. Guess which of those commands would tell you where those 2 lines meet. Nope. Which of these things means where lines meet? Intersect. So then, and then you go 5, and then, okay, first curve. Now get closer to where the lines meet that you want to find. So I want the left place where they meet, so I might even go past it. Hit enter, and then the second curve, and then hit enter, and it'll tell you the same numbers we just saw, 0.55, or 0.549. And then repeat the process, but move the cursor closer to the other meeting point, and it'll do it for you. And that's it. Then it asks you the same thing that it asked us on the last example. When is the ball 25 meters above the ground? Never. It doesn't get that high. So, trick question, don't fall for it. And there we go. There's 7.8 stuff. Okay, why don't you try the skier guy? And I don't care, if you don't want to use the TI, which most of you don't have to worry about this stuff. You just have to plug in the equation and answer all the questions. So see if you can do that. We'll go over it tomorrow, and then we'll also maybe go over the last couple pages here. And then whatever time's left after that, you can just work on homework, because there's only 2 more examples here, and they're pretty easy now that I've shown you all the steps. So I'll stop the video there. We'll go over this question tomorrow, and the one after it, which apparently is a blank page. Oh, there it is, one after it, where you have to type this into your Desmos or your TI and then make me a sketch. tell me all the answers to these questions. And there's a third example. So there's 3 more examples to go. So do those for homework, and we'll go over them tomorrow, and then I'll give you work time on the textbook and the review after that. Okay, so that's the class for today.